This is my fifth video on AS Quantum Physics, and it's about path integrals. How do we calculate the probability of a photon or any quantum particle arriving at a certain place? Well, here is a photon, Freddy the photon, and Freddy the photon has a frequency f, and associated with the photon we say there's a thing called a phasor, and a phasor is a rotating vector. If you imagine a little arrow which is whizzing around anti-clockwise, and it has the same frequency as the photon. At the beginning of the journey we imagine the phasor is pointing upwards, and then as the electron or the photon goes on its journey, the phasor whizzes round and round and round. Okay, our photon begins its journey at point A, and what we're going to do is calculate the probability that it will arrive at a point B on a screen somewhere. So my photon is going to go from A to B. What's the probability it will arrive at B? Now, the most obvious path is the straight line from A to B. If the photon travelled this straight line path at the speed of light, what we can do is work out the direction that the phasor would be pointing at the end of the path. At A, our phasor is pointing upwards, our phasor whizzes round and round and round, and when it arrives at B, it'll be pointing in some other direction, probably, before and after. Now, what we do is we do the same thing but for every possible path from A to B, and we work out the direction of the phasor at the end of each path. This is no easy task because there are an infinite number of paths from A to B. There's the very, very obvious one, which is the straight line path. There are some which are quite straight, and then there's lots and lots and lots of weird ones. And our job is to work out where the phasor is going to end up at the end of each of these paths. And when we've done that, what we do is we find the resultant. We add all the phasors together and we find the resultant phasor. This is obviously impossible unless you consider this, that basically we only need to consider the more obvious paths. If we line up all the phasors for all of the paths in a certain way, we get this diagram, this curly Q diagram, which has the curly bits on the end and a kind of straight bit in the middle. Now, all the arrows in the straight bit, they're the more obvious paths. Okay, those paths tend to take about the same amount of time, so the phasors for those paths tend to point in roughly the same direction. For every weird and wacky path, there is another weird and wacky path where the phasor ends up pointing in the opposite direction, so they all cancel. Basically, the phasors for all the random paths will tend to cancel out, and the paths that make the most significant contribution are the ones that take about the same amount of time, which is usually the least amount of time, and these are the most obvious paths. Conclusion is we only need to consider the most obvious paths. Looking at this situation here where we have a double slit, how many obvious paths are there from A to B? And the answer is 2, through one slit and through the other slit. Now, the diagrams below represent how the two phasors might end up. They might end up pointing in the same direction, in which case the resultant would be big. They might end up pointing in opposite directions, in which case the resultant would be 0, and then any other combination in between. For example, if the two phasors were at 90 degrees to each other, then the resultant would be at 45 degrees, and its length would be √2 times the length of one of the phasors. So we can work out the probability of a photon arriving at a certain place on the screen, and the probability is proportional to the amplitude of the resultant squared. So we find the resultant phasor, We measure its amplitude, and then the probability is proportional to its amplitude squared. Don't forget the squared. And if we do that across the screen, what we find is that there are places where the photons will probably turn up, and there's places where they will probably not turn up. In other words, it explains our pattern. The method seems very strange, but it's actually very, very powerful, because it explains why the pattern builds up over time, even if there's only one photon or one electron in existence at any time. Okay, here's an exam question that you might like to have a go at. Have a read, have a go, and the answer in 3, 2, 1. Okay, the probability is proportional to a squared. For x, the amplitude of the resultant is 2, so the probability is proportional to 2 squared. For y, the amplitude will be root 2, so the probability is proportional to root 2 squared. So the ratio of the probabilities will be 4 to 2 or 2 to 1. Richard Feynman came up with most of this, one of the pioneers of quantum mechanics, Richard Feynman. There are certain situations where Newtonian mechanics can't explain what's going on, and weird things happen. And one of these situations is when things are very, very, very small, like electrons and photons. We say they are quantum particles, and to explain their weird behavior, we need quantum mechanics. The other situation, which I've looked at in other videos, is when things are traveling very, very fast, and for that we need special relativity.